Okay, so let's start again. So welcome everybody to this very last session of the day, which will be devoted to funny subject like testing general relativity or exploring new physics and maybe new exotic sources also. So there will be 3 talks and then after a discussion session. So the first talk will be given by Chris. So Chris.
Thank you very much. Also, thank you for the kind invitation. It's really nice to be here where it is a nice town and also 10 degrees Celsius warmer than where I'm coming from. So indeed, testing general relativity with gravitational waves. So, and then the slide transition doesn't work anymore, of course. Yeah, okay. So this slide I probably can go over very quickly. So here are the detectors that we have currently. This was the first detection of gravitational waves. So we, at least for binary black holes, we have a reasonably multiple waveform models that are mathematically reasonably well understood, and also accurate enough for the current detectors, probably not for Einstein telescope or LISA. But basically, you have the in-spiral, the merger, and the the in-spiral, the merger, and the ring down regime for binary black holes are in GR reasonably well understood. We also by now have a rather large number of detections, which of course keeps growing. We're above 200 now. Now, in terms of fundamental physics, what is this good for? Well, that is illustrated by this plot. So let me explain what you're looking at. So on the horizontal axis, you have a characteristic time scale, a radiation reaction time scale. And on the vertical axis, you have some measure for how strong space-time curvature is. Now, the bottom right, very long time scales and very low curvatures. This is where we live in the solar system. And from the perspective of testing general relativity, that's actually the most boring place to be, right? Things are not dynamical at all. They take enormous time scales, and also the curvature is very weak. Until very recently, until 10 years ago, actually, binary pulsars were the most general relativistic objects known. But now we are in the top left corner, have access to the genuinely strongly curved dynamical spacetime, thanks to binary black hole and also binary neutron star detections to some extent. So this is where we are, and this is what we want to exploit. Now, a bit about the nature of gravity, and in that sense, it is worth mentioning Lovelock's theorem. I have the mathematical formulation here, but it's easy to translate into physics or astrophysics terms. So in physics terms, what does Lovelock's theorem say? Well, if you want a theory of gravity that is in 4 spacetime dimensions, where gravity is governed by a metric tensor and no other field, if you want dynamical equations that are up to second order in derivatives with respect to time and space, if you want general coordinate transformations, and if you want some sense of energy momentum conservation, then the only field equations you can end up with are the Einstein equations with the option of a cosmological constant, and that's it. But that also means that as you drop one or more of the assumptions that go into the theorem, then you free yourself up, and then a zoo of theories emerges. So for instance, string theorists like higher dimensions, fine, then you're not confined to the Einstein field equations anymore. There are people who like extra field for a variety of reasons, like besides the metric tensor, you can have a vector field or a scalar field. This has been done, among other things, to try and find a dynamical explanation for things like dark matter or dark energy. So rather than dark matter being a kind of particle, it could be a modification of gravity and so on. But this zoo of theories or models makes it difficult for gravitational wave observers such as myself to find out waveforms available for general relativity. So, That's fine for me. Yeah, that's the safe option. Okay, so strong field dynamics of space-time, but one can also think of other things like the propagation of gravitational waves over large distances. And then I'll get into that, but basically, according to general relativity, gravitational waves do not experience dispersion in a vacuum, but maybe there is such a thing in alternative theories. And then something that is becoming more and more interesting because more and more accessible to observations is what is the nature of compact objects. So when we see very compact objects merge with masses of a few tens of solar masses, how sure can we really be that these are the black hole, the standard Kerr black holes of general relativity? And then one can look for, so this can be viewed as kind of a summary for the rest of the talk. One can then think about, are there unexpected effects during the inspiral? Is the remnant object of the merger consistent with the O'Hare conjecture or with the area increase theorem? And one could search for so-called gravitational wave echoes, but this is something that I'll come back to. And it doesn't want to change. Okay. Yeah. Okay. So first, the strong field dynamics. So, like I said, we do model or theory independent tests, which means that we start from general relativity and introduce deviations. Now, first of all, this is the phase during the inspiral as a function of a characteristic velocity, which you can write as a kind of series expansion, where the objects in red are functions of the masses and the spins of the two objects. And functions you can calculate and you can view as predictions of general relativity. So now you can think of allowing for variations in each of those coefficients or those functions and place bounds on these deviations. And this is a plot, some version of which you will have seen before. So the blobs are probability distributions based on the data for the different parameters that appear here and also in the merger ring down actually. And so if GR is to be correct, it had better be the case that all of these probability distributions are consistent with zero, which so far is the case. Now, there's rich physics in here. My favorite coefficient is this one, 1.5 pn, not only because it is the best measured so far with 10% uncertainty, but also that is where that's the lowest order in this expansion where the dynamical self-interaction of space-time kicks in. That's important physics. And also spin-orbit interactions, and then starting from 2 pn, spin-spin interactions, and so on. Now, something that will be a recurring theme in this talk is you can combine it. Typically, you can combine information from multiple detections to get either more stringent bounds on deviations from GR or eventually find a deviation from GR. And in fact, bounds will get tighter roughly as 1 upon square root of the number of detections. Okay, so now earlier in this meeting, the question was asked, so is LVK only doing model independent tests? And generally the answer is yes, but people are doing tests also on real data. And here is an example of a theory-specific test with the event GW 230529, which was a neutron star merging with a lower mass gap black hole probably. Now, this gave us the strongest constraint to date to the -1 post-Newtonian coefficient. So other than the coefficients that appear in general relativity, you can also have negative ones that would be new. There is a particular theory, Einstein-scalar Gauss-Bonnet theory, that will give you such corrections, but also higher order ones. So now one thing you can do is you can take our so-called model independent tests and then the 1pn coefficient is called like this, and you can connect it to a parameter in the theory, which is a length or a mass scale LGB here, and then do inference on LGB and see what kind of bounds you get. And so this is what you get: the different histograms or our probability distribution on that parameter using different waveform models. Then you can say, oh, something happened here, sorry about that. But then you can say, I really want a theory-specific test, and I want to add corrections, and corrections for this theory are known up to 1.5 pn. And what you'll find then, it's not legible, is the best bound so far on this LGB parameter here, which is smaller than half a solar mass. There's also laboratory tests that have been done for this theory. This bound is 12 orders of magnitude better than the laboratory tests. So for this, you really need to be in the strong field regime. So that was the in-spiral merger ring-down dynamics of space-time. But again, one can also look at the propagation of gravitational waves over large distances that they have to travel from the source to us, the observer. And so a question one can ask is, do gravitational waves experience dispersion? And so one reason for dispersion could be that the graviton mass is non-zero. Now, of course, what we observe is not gravitons. We observe classical gravitational waves. But even so, if the graviton mass is non-zero, also in the classical regime, this has repercussions, namely dispersion. So if you do a Fourier decomposition of your gravitational wave, then you will see that some Fourier components travel at different velocities than some other Fourier components, whereas in GR, all of them travel at the speed of light. So that means the shape of the wave gets deformed as it travels, and this effect is cumulative over the huge distances that the wave has to travel from source to observer. And so you can dig very deep, and indeed we obtained a very stringent bound on the mass of the graviton, something times 10 to the minus 23 electron volts, which, by the way, is several orders of magnitude better than the best bound on the mass of the photon, which also is supposed to be massless, of course. Anyway, we're proud of this result, I guess. And then you can go nuts. You can go for more general forms of dispersion. So a massless particle in GR, like the graviton, would have a dispersion relation E squared is P squared C squared, where E is energy, P is momentum. But you can add some generic term where you have some power alpha of momentum, and then capital A that sits in front gives you the size of the violation. And then, well, you can look at the size of capital A for different choices of this parameter alpha inspired by different alternative theories of gravity. And here too, you get extremely stringent constraints. So the size of the GR violation typically for different values of alpha is constrained to be in the order 10 to the minus 20 pico electron volts to the power 2 minus alpha. So very strong constraints. Now, also related to the propagation of gravitational waves, this is a multi-messenger workshop, so of course I have to have a connection with electromagnetism. One can ask, does the speed of gravity equal the speed of light? And as you've probably heard, well, the binary neutron star from 2017 came with a gamma ray burst 1.74 seconds afterwards, and that allowed you to place both a lower and an upper bound on the relative difference between the speed of gravitational waves and the speed of light. And also these bounds are extremely tight, right? 10 to the minus 15, 10 to the minus 16 relative difference. And this one measurement excluded a whole bunch of alternative theories of gravity that were designed to explain, like I said, either dark matter or dark energy in a dynamical way as a GR violation, rather than having to invoke a new particle or a new field. So that's all very interesting, but what is getting even more interesting now, again, because of detector sensitivities increasing, is what is the nature of the compact objects? So again, these tens of solar mass compact objects that we see merging all the time now, we think they are black holes, but how sure can we really be that they are the standard Kerr black holes of general relativity rather than some more exotic objects? More exotic objects, by the way, have been cooked up in the literature in spades. So there's boson stars, dark matter stars, What I mean by them here is, suppose that dark matter is composed of fermions, then they can form star-like objects that are held up by Fermi degeneracy pressure. And if they're compact enough, they can look like a black hole. Mentioned already were clouds of ultralight bosons surrounding black holes. Then it gets more and more exotic. Gravis stars are pockets of de Sitter spacetime, so spacetime that wants to expand but is surrounded by a shell of matter or a shell of whatever that holds it together. Is such an object very plausible? Probably not, but okay. And then there are wormholes and firewalls and fuzzballs. Now, are any of those things plausible? Well, boson stars are not a crazy idea, but even so, if you want a boson star to mimic a black hole, you will see that in any bosonic theory that is self-interacting, you will have to kind of fine-tune the mass of the boson and its self-coupling in such a way that you can have boson stars that are compact enough to look like a black hole, but are not so compact that they immediately collapse to a real black hole. Okay, so even boson stars are from that angle a bit suspect. But my perspective on this is what we're really after is the unknown. But what all these things, some of these weird things in some cases in the literature, what they can tell us is, are there maybe generic effects during the in-spiral that will typically be there for something that is something other than a black hole? Something that has no horizon is what is really meant by that usually. During the in-spiral or during the ring down of a newly formed object, etc. Are there some generic features that we can extract and then go look for those in a targeted way? This again is a summary for the rest of the talk, but one can of course look for anomalous effects during the in-spiral. One can look at the ring down of the resulting object, resulting from the merger, and then there are these gravitational wave echoes that would come out after the merger has taken place for objects that don't have a horizon. Okay, so let's go through these in turn. So what could be an anomalous effect during in-spiral? Well, here we can take a cue from neutron stars. Neutron stars, as they get closer to each other, they tidally deform each other. And so a quadrupole effect is induced in each of the two stars because of the tidal field of the other. And the pointer isn't so good. This quadrupole moment that is induced by the tidal field of the companion, there's a proportionality between the two, which this lambda here is a function of the equation of state, the internal structure of the object, and the mass. Now, to the approximations made or implied here, black holes will have a lambda of identically zero, tidal deformability identically zero. Boson stars, dark matter stars will have a positive tidal deformability, and gravis stars will have a negative one. Now, tidal effects, and this was mentioned before also, I think, they enter the in-spiral phase at a very high post-Newtonian order, or in terms of velocity, order v by c to the 10th power beyond leading order. So it may seem hopeless to find these things. But the fortunate thing is, the way this tidal deformability lambda enters is through the combination lambda divided by mass to the 5th power. And so that can be quite large. It could be order of 1,000 for neutron stars. We don't quite know yet. But this can also lead to measurable effects for things that are black hole mimickers, such as boson stars. They are tidally deformable. And depending on the type of bosonic field or theory you assume, you can see that you may see that tidal deformability. Another anomalous effect you may have during in-spiral is the following. So the Earth turns around its axis and causes a centrifugal bulge. The Earth is bulging around the equator. Now, for something made out of matter, generic things made out of matter, such a thing will happen, for instance, also for neutron stars. But it will also happen for things like boson stars, so certain black hole mimickers. And in fact, again, a quadrupole moment is being induced by the fact that you have this centrifugal bulge. My pointer doesn't work, so I'll point with my finger. But it goes like some constant kappa. Chi squared is the square of the dimensionless spin, and then m cubed is the cube of the mass. This enters at second Post-Newtonian order, so we have a better chance of seeing it, I guess. For black holes, this constant kappa is identically 1, again, to the approximations made. For boson stars, dark matter stars, this should be greater than 1 rather than greater than 0, and for gravastars, smaller than 1. So again, you can allow for deviations delta kappa from the black hole value of -1 and look at presumed binary black hole events. And then for delta kappa, these are the kind of probability distributions you end up with based on the data from a couple of interesting gravitational wave events. There are two colored curves in here. Never mind what the difference is. Different assumptions, simply physical assumptions. But the point of this plot is the range is very wide. So if this is if this is a measurement on a relative deviation in something, you might say, oh, that's a very crappy measurement. Well, yes, in a sense. Except that for boson stars, which I keep going back to, possible values for kappa range between 10 and 150. And so this already is starting to become an interesting measurement. Something that also will be a recurring theme in the rest of this talk is that, okay, so with current detectors, there are certain things where we can make precision measurements. I mentioned the mass of the graviton, which is measured with fantastic accuracy, but pretty much everything else, the accuracy is kind of crappy. So we're going to need a bigger boat, and the bigger boats, 2, will be LISA, Einstein Telescope, and 3, Cosmic Explorer. But we are here in an exploratory phase where we can see gravitational waves, but we cannot yet extract that much science out of them. Let's move on. The ring down of a newly formed presumed black hole. So if you're really dealing with an ordinary black hole, then when a newly formed black hole, when you have such a thing, then in the ring down regime, what you get is the Kerr metric or you can model it as a Kerr metric with linear perturbations on it. And then the gravitational wave signal from the ring down looks like this. It is a superposition of damped sinusoids that come with some characteristic damping time, tau LMN, and some characteristic frequencies. Now, in GR, there is the no-hair conjecture, which says that if you have a stationary black hole that is electrically neutral, then its space-time is completely characterized by its mass m and its dimensionless spin chi. Now, of course, stationary black holes do not emit gravitational waves. We won't see anything. But if you have perturbations around a black hole, such as in the ring-down phase, then these characteristic frequencies and damping times, they in linearized general relativity, but now a linearization around the Kerr metric, they become specific functions of the mass of the final object and the dimensional spin of the final object. And once again, you can do tests. You can allow for relative deviations in these dependencies on the final mass and the final spin. So let's go to the results again. So these are results from recent measurements. By the way, you have many such frequencies and damping times characterized by LMN, which give you the number of a spherical harmonic. Okay, so that's all LMN are. And the strongest modes will be the 2-0 modes. So here's a measurement for relative deviations in the frequency and the damping time for the 2-0 mode in the ring down. The two blue contours enclose 90% of probability for 2 black holes whose ring down was reasonably in our most sensitive frequency band, so that's why they were picked out. But once again, you can combine information from all of the detections you're going to make and end up with a tighter bound, and that is this gray blob here. So this is a combination of information from many ring down signals from presumed binary black hole mergers. The dashed lines indicate the GR values. We are not declaring a GR violation yet. Again, this is a 90% probability contour, right? So we're not even at 2 sigma here. But okay, so this is the kind of accuracy we are getting here is in the order of 10% in terms of this frequency and about 10% in terms of this damping time. Again, not yet fantastic, but we're doing interesting stuff. Then echoes. So if you have a black hole mimicker that has no horizon, then echoes can happen. So what are echoes? Okay, so in the case of ordinary black holes, the gravitational waves that go inwards and past the horizon will never be seen again, of course. It's only the outgoing gravitational waves that can ever reach a detector. But now replace the black hole by something that doesn't have a horizon, then what can happen is the ingoing gravitational waves inside the object will bounce back and forth multiple times, and each time they reflect on the inside, a burst of radiation comes out, and these are these echoes. So this happens after the ring down. You can have bursts of gravitational waves coming out. Now, there's something interesting about these echoes, namely, if you look at the time interval between successive echoes coming out, delta t, this is a fairly generic expression for it, where little n is some constant, which is determined by the nature of the alternative object. M is the mass of the object, and little l here is the length scale associated with the horizon modification. So there's no horizon there anymore, but typically there is some length scale associated with whatever structure replaces the horizon. Now let's plug in some numbers. So for n, yeah, we choose something. An empty shell would be n equals 4. We put in 4, fine. That's not so important. But we could take the mass of GW 150914. The final mass was 65 solar masses. We stick that in. Now let's assume that the fact that you have not a black hole but something else, let's assume that it is due to a macroscopic quantum effect. Then it is reasonable to set the horizon modification scale, little l, to the Planck scale. If you stick in the Planck scale here, you get a delta t in the order of 100 milliseconds. And that's interesting because 100 milliseconds is much longer than the typical duration of the ring down. So your echoes will not be drowned by the ring down signal. And on the other hand, it's also not a million years. So it's worth looking for these things. And we did. So what you see here is a morphology-independent search for echoes. We don't know if there are echoes, what shape they will have. The shape will presumably depend on the nature of the object. So we don't assume a shape here. So each time you see a box with gray in it, the gray is raw data. And red is the reconstruction of a possible echo signal. Do not get your hopes up. Let me say straight away, the top left box is a simulation. You do see echoes there. This was to check that our analysis method worked. But unfortunately, so far for all these other real gravitational wave events, it's flat lines. You don't see echoes. Now, another thing you can test is Hawking's area increase theorem. So during binary black hole merger, it should be the case that the total horizon area does not decrease. So for the two ingoing black holes, if they're far enough apart, you can consider them Kerr, and the area of the horizon we have an expression for in terms of mass and dimensionless spin. And of course, there's two ingoing black holes, so you have to take the sum of the areas. By the way, how do you measure the masses and the spins? Well, from the in-spiral signal, we know how to do that. And you stick in, well, a probability distribution for those values. The final black hole, if that is also Kerr, then again you have a formula in terms of the mass and spin of the final black hole. And to get those two, you can look at the ring down frequencies and damping times, which, remember, are actually functions, well-defined functions of those two quantities. And then according to the area increase theorem, it should be the case that the relative area change is non-negative. And let's see whether that's the case. So here's a measurement on GW 150914. So here's the relative change in area. The shaded region in this curve is forbidden by Hawking's area increase theorem. And then again, you see two curves here. Again, they correspond to different assumptions. But the important bit is that in both cases, about 95% of the probability lies in the safe zone. And so Hawking's theorem, and therefore GR, passes with 95% probability. Now, again, this is not yet a precision test, and I keep emphasizing this, but even so, we're starting to get into very interesting territory. In the 1960s and 70s, when the no-hair conjecture was developed, when the no-hair theorem was proven, etc., I don't think, well, we can still ask Penrose, I guess, but I don't think these people believed that during their lifetime, these things would be measurable, testable at all. So I already find this fantastic, but still we want to do better. And better is, well, going to be Lisa for sure. I don't have to explain what LISA is anymore, I think. But one type of source that interests me in particular is a supermassive black hole surrounded by something much lighter, in which case you have all these, these crazy orbits you could never have in Newtonian gravity. This will turn into a precision test of GR, I think. And then, of course, Einstein telescope and Cosmic Explorer. Now, an important thing is Einstein telescope will be more sensitive by a factor of 10 than the current detectors, ground-based detectors at their final design sensitivity, but there'll also be in the order of 100,000 detections per year. And remember that a lot of tests of GR, you can combine information from multiple sources, and your accuracy will get better with the square root of the number of detections. And so this is, and moreover, for those tests that depend on distance, like propagation of gravitational waves over cosmological distances, you'll also be able to see, well, to the edge of the visible universe. So this is a summary. I won't read this in detail, of course, but I hope I've convinced you that we have first access now to the truly strong field dynamics of vacuum space-time, which we did not have access to 10 years ago. Propagation of gravitational waves over large distance, probing the nature of compact objects, and I had some highlights, and I want to emphasize that, yes, we're getting somewhere. We're getting into truly interesting territory that Hawking would have appreciated, I think. But really, now we want to move to high precision science, and that's going to be the next generation of gravitational wave detectors.
Thank you very much, Chris. So we have time for questions. Yeah.
Thank you for the nice talk. I have a question / comment on the issued results for the Gauss-Bonnet theory length scale.
Yeah.
So I guess that result is done by changing only one parameter at a time and fixing the other PN deviations.
No, so there are two tests in this picture here. So one test is where you change only one parameter, namely the leading order one, and that's it. And then you connect that with this length scale, you get some result. But in the other test, there you really calculate up to 1.5 PN what the deviations in inspiral are coming from this theory, and then you simply include them, and they will be functions of LGB. So they will give you extra information on LGB.
Yeah. Thank you.
Other question? Yeah.
Thanks for your talk, Chris. The question I wanted to ask was about the gravitational wave echoes. So I noticed on the plot, at the bottom left, you had 170817, which is obviously a binary neutron star, and you said that we would maybe expect to see these echoes for compact objects that don't have a horizon. So is there I think it was the next slide.
Okay.
Is that, the bottom left, is that 170817, I think?
No, the binary neutron star is 170817. Yes, it actually is in there.
Yeah. So is there a straightforward reason as to why we wouldn't see anything for a binary neutron star at this stage?
No, there's no reason why you wouldn't. So the general belief is that a binary neutron star merger, I'm going to tread on people's toes here, but many people believe that a binary neutron star merger eventually leads to a black hole, or a black hole mimicker is, the question here. And then you might again see echoes if the final object has no horizon.
Okay. Yeah. Thanks.
You show here the results up to GWTC2. Have you done the search of echoes also for GWTC3 with the new?
Yeah, some of the. This is from GWTC3, I think.
GW2001.
So yeah, the date makes sense at least. Yeah. So it is the case that some of these results are kind of old, but that is because there was quite a break between observing runs, right? And COVID came in between as well. So there's much more to come. There's more accurate results to come than the ones I can show here.
Thank you.
Yeah.
Hi, thanks for the nice talk. As you said in the end, so with new detectors, we will have tighter constraints, and we can also have them more shrinks by combining the events. So for that, how much are you worried about waveform systematics?
Very.
And do you think, just general comment,
Yeah.
so the direction for waveforms should be on adding more astrophysics or something else?
Better accuracy. So I think for a long time to come, unless we do see exotic objects, the baseline waveform and the baseline type of event to do tests with will be binary black holes or binary black hole mimickers. And so what will be needed for sure, we already know this, is more accurate inspiral merger ring down waveforms than the ones we have now. As you probably know, what we have now is a bit of a Frankenstein's monster, right? You start with the post-Newtonian inspiral, you take input from numerical relativity, you try to cleverly, hopefully, bridge the plunge and merger regime, and then, of course, in the late ring down, you have perturbation theory again. But yes, we need better waveforms. And to give an idea, so to give an idea of the kind of better accuracy for most tests of GR you will get. So let's stick to ground base. So for Einstein telescope, you have a factor of 10 improvement in sensitivity, but you also have a bigger bandwidth, a frequency bandwidth, which it turns out for most events, binary black hole events, buys you another factor of 10. So now you're more accurate by a factor of 100. But then you see many, many events. Let's be pessimistic and say 10,000 events only, so that the square root is not too difficult. Square root of 10,000 is another factor of 100. So now we're a factor of 10,000 in principle more accurate in all these measurements than we are now. And then we are in the precision era. But our current waveform models, they really don't reach there, right? And they're very far off, in fact, indeed. So there's a lot to do for theoretical physicists. Yeah.
Other questions?
On Zoom?
Maybe on Zoom? I have one concerning the dispersion. So you said that the dispersion was much more precisely measured for gravitational waves compared to electromagnetic signal. The fact that electromagnetic signal propagates eventually with the dispersion.
Yeah.
Because there is a relation between the velocity and the dispersion, because basically the velocity is just c divided by the index. Can we translate somehow the constraint that we have on the dispersion for gravitational waves to a constraint for dispersion for the electromagnetic waves?
No, I don't quite see how, unless you also see the gravitational, the electromagnetic wave, as we did, of course, in the case of 1708-17 with the gamma ray burst. But I don't quite, I don't immediately see how a result that only comes from gravitational waves, so not this, but looking at gravitational waves from binary black holes, how a result that only comes from gravity will translate to electromagnetism. That, yeah.
Because the speed of light and the speed of gravity is the same. If there is a relation between dispersion and the speed, if you have the same speed, you should.
I see. You can do the translation in principle and compare this result with this one. This is of course about speed and does not assume the mass of a graviton or some other specific alternative dispersion relation. But if you assume mass of the graviton, then this is the winning number. Yeah. And the reason is that, here you can use binary black holes whose waves have traveled over a humongous distance. And again, this presumed dispersion effect is cumulative over distance traveled.
Thank you. One more question for Chris.
Zoom?
Il y a quelqu'un sur Zoom qui veut? I think someone is trying to speak. Zoom question. Yeah. Can we
Yes.
hear you on Zoom?
Can you hear me?
Yeah.
Yes.
Yeah.
All right. Thank you for a very informative talk. I have a simple question with the current observations. Apart from the mass, do we see any difference between the neutron star mergers and the black hole mergers in terms of the gravitational wave signal?
Well, in the case of binary neutron stars, we of course only see the in-spiral because the end of in-spiral happens at 1500 hertz approximately, where our current detectors have have no sensitivity actually. So that is a difference. With binary neutron stars, you can test general relativity, but you can only test the in-spiral. Also, if we were to see with future detectors, we will actually, with Einstein telescope, we will have access to the merger of binary neutron stars. The merger of binary neutron stars will look quite different, of course, from the merger of binary black holes. And there we will have the difficulty that there will be a degeneracy between us not knowing what the equation of state, the internal structure of neutron stars is, and maybe there being a GR violation.
Thank you.